Okay. Hi. Hi, guys. Again, another Friday quantum hardware course. So today we will still talk about like the Kerr media, nonlinear media, but today we see some quantum properties. So because we have like a lot of things to show, I don't have slides today. So I will start. I'll start with the whiteboard, and I'm planning like to finish this part of the course in the next Friday. So in the Friday next week, right? So in the next two Friday we start the third part that is talk about like the optical cavity and discuss a little bit about quantum electrodynamics with more details. That's the last the last optical models that we see in this course, and then we return after, I don't know, maybe one pause, like to talk about ion traps. But I mean, we still have a lot of things to do. So this last part will be the longest. So probably will be 1 month, 4 or 5 lectures, maybe, to see like the quantum electrodynamics part, optical cavity part. So okay, so let's continue from last talk. Remember that in the last, so today we'll talk about nonlinear care media, and we see like last the last talk we discuss, we make a summary about the classical part, and today we see some quantum properties and some of the properties that we can use to do computation. So we saw like the most important effect of a care media is what we call the cross phase modulation. Modulation. And we'll define what's this. See. So what it do it that it provides between two modes of light. Plus, that just a moment, if someone is ringing the bell.
Bamborde joined.
Oh, okay. I will stop a little bit just to someone is ringing the bell here, but I return soon. Let me just.
I didn't see anything on the chat. Oh, I see. It must be a bell from that pesky so-called real world.
Hi. Okay. I'm back. Sorry. Some else things. Okay, let's return. So the cross-phase modulation provides between two modes of light that is classically described by the N2 that we saw in the last lecture, N2 term in equation 719 from Nielsen Schwenk book. Equation 719 is this one that we found in the last lecture. The 2I, where I is the intensity that's proportional to the square of the amplitude of the electric field. And this eta 2 is proportional to chi 3, right? So eta 2 we saw is proportional to chi 3. This susceptibility, third order susceptibility, and E is the intensity is proportional to the field. I is proportional to the electric field, the amplitude. I think it's square. Okay, and this is the nonlinear term in optics, right? That is related with the polarization vector. Just to remind you guys, the polarization vector written in terms of chi 0, chi 1, chi 2, e squared, chi 3 e to the third, and from no, and this keep going. And for centrosymmetric materials, chi 2 is in general 0. So this is the nonlinear, the main nonlinear contribution. This is the linear term. This is the first nonlinear contribution. Okay. This for centrosymmetric. We saw this last lecture. At least a summary. Centrosymmetric material. Okay, and this is from last lecture. Okay, but this is the term that we are interested now. And we are this term here that we found, it is interaction between photons mediated by atoms in the medium, in the Kerr medium. Remember that I told you that the equation like that, this is phenomenological equation. You can doing phenomenology, we see that this equation is right. But you also could use like first principles to determine the equations related with quantum optics. And one is see if you consider like the quantum mechanics effects of the atoms that compound the Kerr medium, and we can find like most of the equations that you can show phenomenologically that these equations are right. So. But yeah, these details, like in the calculations, how we do this, like using first principles, the theory we didn't discuss so much. But if you still have time, maybe next week we discuss a little bit more. The book that I recommend, I told you last week, but my camera was with problems, is this one, Nonlinear Optics. Okay, the Boyd book. Okay. Okay, but this so far is what we are interested. So quantum mechanically, this effect, like that, this effect, the cross phase modulation, is described by the Hamiltonian. Define the Hamiltonian of XPM from cross phase modulation as chi A daga A, B daga B, where this XPM means the cross phase modulation, and A and B are two modes propagating through the medium. And chi is like the term proportional to the chi tree, right? The nonlinear term. That you could write like the Nielsen Schwing don't give so much details. He just write this as H bar K. He put only K, but you use K for another thing. So this is just this K here is just K bar. It's just a opening constant. That in general is proportional, for instance, for the electric charge of the atoms that are present here. The total electric charge. But maybe in the next week, we see some details, more details, how to evaluate these and the central symmetric materials, okay? So, but in general, to do computation, what we consider, like if I have a Kerr medium, we have two modes, mode A and mode B, propagating from this medium of size L. Okay? Okay. And for a crystal, one medium like this, right? Of size L, we obtain the unitary transform. That I will call now K, using like the notation. That's my operator. This K here is just a constant. So K is exponential minus I x cross-phase modulation times L. L is the size of the nonlinear medium. Okay, so let's see some consequences of this new operator here. So by combining the Kerr media with beam splitters, we can construct a CNOT gate. So let's see how to do. So let's see first the properties of this operator when we applied for the modes A, B. So for K, let's change the column. K applied to this state, 0, 0. This is the state where I have no photons coming from A and B. This evidently will not change. So this should be something like this, okay? Because no photons is coming here, so nothing will happen. But let's see if this definition agrees with our like physical suggestion. So this KL and HXPM is the chi and dagger A, B dagger B applied to this, expanding this exponential. This is just IL and dagger A, B dagger B plus higher order terms applied to 0, 0. In the convention that Nielsen-Schwenk use, remember, this is the mode A, and this is the mode B. So this operator applied for this one, and A applied for the second one. So this is just 0, 0 plus IKL, and when I apply the destruction operator in the mode 0B, this will be 0, and this will contribute with 0, right? So this is just like 0, 0. Okay, that is what we expect because no photon is coming in the medium. So by now, let's see what happened when I have like K, and I have no photon in mode B and one photon in mode A. So we do this again, apply, say, B dagger B, 0, 1, make the expansion, the same thing, and dagger A, B dagger B, high order terms, 0, 1. And this will do the same because see, this term times this operator here, that's identity, 0, 1 plus IKL. So B we apply B for this first term, the 0, and this will give like again 0 because the destruction operator applied here will be 0. So we have 0 multiplied for something. So it's 0 again. Okay. So when I have only one photon come from one of the modes, it doesn't change anything. It's the same. And you can prove this if you use k applied for 1, 0. This will also do the same thing. We see that this is 1, 0, doesn't change anything. So it will in fact just change something when you have one photon come from mode A and one photon come from mode B. When you do this, we found that the result is this one. And we can see, like, let's see this, I, chi, L, dagger A, B, dagger B, applied for 1, 1, expand, I, chi, L, dagger A, B, dagger B, high order terms, 1, 1. So this is 1, 1, plus I, chi, L, and now B, the destruction will like annihilate this photon, you have 0, but then you have the creation. The 0 will become 1. And the same thing for A when applied here. So this will be 1, 1 plus high order terms. So in the end, we have 1 I chi L, high order terms, 1, 1. And this is the exponential expansion. So this is what we found here. I chi L, 1, 1. So the operator K will just change this state 1, 1 when we have like a photon comes from both modes, like the port A and the port B. Okay, and we can now consider, oh, okay, and if chi L is equal to pi, if you do this, we'll see how you can like build uh, a CNOT gate. So when this is equal to pi, we have that k, this is k 1, 1. So k 1, 1 is equal exponential I pi is just minus 1. So this will be minus 1. Okay, so this is what we define like the dual rail when we have the two photons coming. Now we could consider two dual rail states. In other words, that is when we have like four modes of light. Okay, so this is a single dual rail. We have this. If we have two, so Nielsen Schwang, he defined new bases when we have this in this case, like two dual rail states. He defined, so these modes lives in a space spanned by the following bases. It just define new bases These bases are here called E00, which is equivalent to 1, 0, 0, 1. And I will explain what he means by this. But just write here the basis. E01, that is 1, 0, 1, 0. This is this basis. The other is E10, 0, 1, 0, 1. And I have this state. And the other basis is E11, 1. And I have 0, 1, 1, 0. Okay, this is what is written in the news insurance, but what he means, let's just do explicitly here, he defined this one. This is the mode B, let's call B2. Okay. So I have 4 modes, right? I have the chem media, and I have like A1, B1, and A2, B2 coming in the media. Okay. So in this, his definition here, so this first term is the term B2. And then times this is the term A2. And this is the term A1. And this is the term B1. Okay? Oh, sorry. So this is A1, and this is B1. This here.
Those are tensor products?
Yeah, tensor product, right. This is the notation, right? When we have this notation here, remember this is like a tensor product.
Oh, thank you.
Okay? So, but now it's 4 terms. So every time that we have this notation, we have the tensor product. So, and he is doing this way, he is defining this, like, remember, we defined this in last lectures. This one, we define our logical L. And this is our logical 1. This was defined like a couple of lectures ago. Now he do the same thing for the first couple. So this is the logical 0. But he is again the logical 0 because he just like flip the terms. And he say that physically he can do this if you put like mirrors in your, when you send this second modes, B2 and A2, you could like flip using mirrors, simple mirrors. This is the definition of logical 1. So for the couple 2, that I'm calling 2, so this logical here is inverted. Okay. So if you do this term here, it's again the same thing, but let's write it more simple way. This is the 2. So this is B and this is A. And this is also. This is the second. For mode 1. So this is A and this is B. Okay? It's inverted. So this is my logical 1. This is my logical 1. And that's why this is the base 1 here. And this is my logical 0 because it's inverted for the first, for the second. So this is my logical 0. Okay, and you can keep going. So this is 1 here because it's 0, 1, and 0 here, 0, 1. But it's inverted. So let's, because this is true, let's write this in another part. It's easier. Yeah, so this term here, E is 0, 0. This is my logical 0, 0. Okay? Because this is 0 and this is 0. So the logical 0, 0, I can represent this as a matrix like this. It's a tensor product of 0, 1. Né? Just remember, 0 is defined this way, and 1, the logical 1, is defined this way. If we have the tensor product of 0, 0, we have a matrix like this. So this is 0, 0. This is the base 0, 1. The base 0, 1 is just the logical 0 and the logical 1. And this product 0, 1 is this, right? 0, 0, the matrix. And we keep going like the 1, 0. The 1, 0 is this one here. Yeah? Because in the first couple, like this 0, 1, this is 0. But for the second, this is 0 logic. And the second, that's this one. 0, 1 is the logic 1 because inverted. So this is 1 logic. That's why is E 0, 0. And this is 1, or the first mode, the first couple, we use like the usual logic gate, logic notation. So 1, 0 is my logic 1. But for the second modes, we invert. So this is the logic 1, 2. Okay. So this one is 1, 0. The matrix notation is this. And the other 1, 1 is 1, 1 logic, which is this. And okay, and we know how K do when applied to these guys. And we could like using this to build the K notation, the K matrix notation. So I know that K applied to the mode 0, 0 is 0, 0. Okay, it doesn't change. 0, 0, which in the matrix notation is this. I know that K, let's write here to save some space. K applied to 0, 1, do nothing, remember? K will just change the 1, 1. So K applied to 0, 1, it's E 0, 1. E 0, 1, which is this. K applied to 1, 0 doesn't change, is 1, 0, which is this. And k applied to 1, 1. That's when k is applied to this state, 1, 1. It's the only one that is different when chi L is equal to pi. We saw that this is 1, 1, which is the same that write this 0, 0, 0, and minus 1. Okay. This let's write this 4 chi L equal to pi. Okay. So we have this 4, and we can like write the matrix for k, right? Okay, will be just like the 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and the other 0, 0, 1, 1. So if you use k and multiply it for each of these terms, you have this. Okay, so this is the matrix representation. And if we remember, it's matrix representation for chi L equal to pi. That's why this is minus 1. And this is useful because the CNOT operation can be factored using K, the matrix representation of K. So if we remember CNOT gate, the matrix representation is this one: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. So this is the matrix representation for the CNOT gate. And we could write this in this form: 1 square root of 2, 1, 1, 0, 0, 1, minus 1, 0, 0, 0, 1, 1, 0, 0, 1, minus 1. We can multiply this matrix for this matrix: 0, 0, 0, 0, 1, 0, 0, 0, 0, sorry, 0, 0, 1, 0, 0, 0, minus 1. This is my K matrix. And multiply this by the same thing here: 1, 1, 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, and minus 1. If you guys recognize, so this is my K. And this guy here is just the identity product to Hadamard. And this the same identity Hadamard. I think we have questions.
No, I was just saying this is really nice.
Okay, good.
That it factors into 2 by 2 matrices, matrix blocks, 2 of which are 0.
Yeah,
And,
yeah,
that's really nice.
yeah. It's a nice idea, right? The guy. And if we remember, we could like write. I think in one of the exercise we did like a couple weeks ago, we showed that Hadamard Hadamard gate could be done using beam splitters, plus phase shifters, phase shifters. Okay, so you could like using like nonlinear optical materials, we could like build like the equivalent of a CNOT gate using like beam splitters and phase shifters because we know how to make like Hadamard gates. A Kerr media, a nonlinear medium, like a type of crystal. And again, this is Hadamard again, so we could use like beam splitters and phase shifters here as well. So, okay. Okay, so and we see one example soon in box 7.4. I think we still have time. So let's just some comments about this. We just put here that this H is the Hadamard gate, just to organize. Questions? No. No. And K is the Kerr interaction. With L equal to pi. So apparatus like that, we'll see apparatus like this one has been considered for constructing a reversible classical optical logic gate. Described in box 7.4, and we'll discuss soon. So just summarizing this part. Summarizing. A CNOT gate. A CNOT gate can be constructed from Kerr media, non-linear media, right? Media. Arbitrary single qubit operations can be realized using beam splitters, and phase shifters. So at least in theory, single photons can be created using lasers and detected, like my input, right? Single photons, I use like lasers, and my output can be detected with photon detectors. So in theory, that's like the basic requirements, right, to make computation. Thus, in theory, quantum computer can be implemented using these optical components. Okay, we will return to comment this in the next Friday. And we see like this is the advantage, right? That it's possible like to make the computation. But in the next Friday, we discuss some drawbacks related to this. Okay. Let's see. I think we have questions, but I would like to show one more example that's present in box 7.4. But questions, please. No? Oh,
Yeah,
okay.
Carlos, I got a question. When you talked about this method could be used to create a CNOT gate, are we talking about a classical CNOT gate or a quantum CNOT gate?
Well,
And is there a difference even? Yeah,
yeah, because here we are using like photons. Maybe what we used here in this example in 7.4, we consider the Fredkin gate, and we see how to reproduce like the classical effects of Fredkin gate. I think in this one, because we choose particularly chi L equal to pi, I think we are reproducing like the classical C notation.
okay. Thanks.
Yeah, because we choose a specific, because we choose a specific angle. If you take in general, so we could have like probably we would have like a superposition or something like this.
I think a classical CNOT would be an exclusive OR, if I'm not mistaken.
Would be what? Sorry.
An exclusive OR operation in classical Boolean circuit. So the CNOT really is a quantum. gate.
Oh, okay. Okay.
Yeah, I'm trying to clarify for Bob.
Yeah, so I'm not totally sure about this. It's like
Yeah, thanks,
this.
George.
And
Because in the example we see here, we could like the Fredkin gate, we'll see like how to reproduce like the classical Fredkin gate. At least, yeah, it's what like building like the we have like the general idea that we use like quantum theory, but for specific, that's why the synod I was like in doubt because here we will see how to I think when the angle is pi, we reproduce like the classical Fredkin. So let's see, let's discuss a little bit here because we don't have so much time. So,
yeah,
but we
I
can.
think an important point is classical, or mostly what's used in classical, is not reversible computing. Once you've done an operation, you can't undo it easily.
Okay.
So once you've done it's like it's like a dimension reduction, and you can't undo it. But the Fredkin gate is a reversible circuit.
Mhm.
Maybe that's what might be
But
called semi-classical.
so, but it's not the case in C naught, right? So,
The C naught is reversible too. That's all of the quantum gates are reversible.
yeah.
But your classical Boolean transistor gates are not reversible.
Okay.
This is one of the advantages of quantum computing that isn't strictly quantum, the reversible nature.
Okay. Good. Good. Thank you. Thank you, George.
And yeah, just to sum up from previous talks, if I'm understanding correctly, the phase shifters can implement the X, Y, and Z 90-degree rotations in different
Mm-hmm.
axes.
Mm-hmm. Yeah, and I think the combination of them in the X, right?
Yeah.
Yeah.
So yeah, when you have then the X, Y, and Z gates plus the Hadamard, then I think you have a universal set.
Mm-hmm.
Yeah, I just wanted to underline the meaning of this, as I understand it, for quantum computing.
Okay. Good. Good.
Or mathematically, that you can use these as a basis for all of the 4x4 operators,
Mm-hmm.
which you showed several slides back. That's when I said nice.
Mm-hmm. Yeah, we could use the combination, right? The
Yeah.
Hadamard and the K. So let's see this example, like the optical Fredkin gate can be built using two beam splitters and a nonlinear medium. As shown in the diagram. So I'll just reproduce the figure we have in the inbox 7.4. If the draw is not so nice, you guys can see there. So it's the care medium. So if I have like a mode, let's call C, in the input, in the output, I have a C prime. And this is the K medium, and associate is like a beam splitter. A beam splitter it's a B operation. So I have here the mode I'll call small b and A. Okay. And in the other part, I have again a beam splitter, but reverse. And here the mode A prime, and here the mode B prime. Okay. So this is the how we can build like the Frelikin gate. So this performs the unitary transforms with the operators that we already know. So I'll call U. U is the operation of B, that's the beam splitter. The cur, it's this operation here for cur, and here B dagger. Okay, where B is for a 50-50, sorry, 50-50 beam splitter. This splitter. And K is for the cross-phase modulation. This modulation. The Hamiltonian that we defined in the beginning. In this case here, K, because it's related with mode B and C, I'll write this way. So I exponential of I, this letter, zeta, B dagger B, C dagger C, where this the zeta here is just chi L. Okay. Okay. So we can see, and here, because this is like the calculation is long, how to show this, I'll just give some hints and we'll have like a homework. So this simplifies to give. So U is, when we use like definition of B, and B is G, let's see. Yeah, you didn't put B here. But we couple of lectures ago, we defined like B. I think I have here. B is like the definition. Okay, you see. B. So this is K, Let's write B here. V is exponential. Theta is the angle. For a 50-50 B splitter, theta is pi over 4. Exponential and then get B minus A B. Okay. So what we need to do is using these guys here, and we're able to find this is just I, A, zeta, sorry, C daga C, B daga minus I, daga B minus A, over 2. Equation 747. And you could also write this as exponential product, exponential with the operators B, daga B, exponential zeta C daga C, and daga B minus B daga minus I pi over 2 B daga B exponential I pi over 2 and daga A C daga C exponential I chi over 2 B daga B C daga C. This is equation 7.48. Okay, how to do this? I mean, we'll not have time to show explicitly all the details, but I can give some hints because it's not so trivial. So you can do this, use the Baker-Campbell-Hausdorff formula to calculate U B K B daga. As we did in lecture 12, page 7. Page 7. If I'm with the lecture 12 open here, just so you guys see the part that I mentioned, is this. We use like the Baker-Hausdorff formula to calculate like B, A, B daga, and we found this expression. And it was like a homework to calculate B, small b, and B daga, and we found this expression. So if you do the same thing here, or at least something similar, because what we have here is a little bit more complicated expression, because if you see, just in the beginning, so U, we could like write in the notation of this, in the lecture 12, we could write this way, K exponential minus lambda G, and we could like expand the K. So this lambda G, if you expand the K, we'll have this I C, daga B, daga C, close other terms, lambda G. And if you do that, if you remember, like this G depends, is for B. So B is related with B is only is B here, the big B, it's here. It depends only on A, small a, and small b. So small a and small b, they they commute with C. So you could write this as 1 plus I chi, that's constant, C daga C, E lambda G, B daga B, E minus lambda G, plus high order terms. So if you do this, you need to calculate this. Okay. In the past lecture, we calculate only. Oh, sorry.
Carlos, you got a little typo. On your green formula for U, formula 7.48,
For
the
8.
second, yeah, 7.48, the second term, either the 1/2 C dagger C, parenthesis A dagger B minus B dagger A, minus B
Oh
A
yeah,
dagger,
sorry.
it should
Yeah,
be
yes.
dagger A.
Yeah. It's dagger here and no dagger here.
Yeah.
Yeah.
Sorry, I didn't want to.
Okay. Just to give, if you do this, I mean, it will be like, at least to me, it was like 4-page calculations. And we don't have time to see everything, but it's the same procedure. We found this. Let me give the answer. This, it will be something like this. I psi C daga C, B daga B, plus I psi C daga C, and daga A minus B daga B, sine square of lambda plus, minus I C daga C, B daga A plus A daga B. And multiplying here is sine of lambda cosine of lambda. Okay? Cosine, sine and cosine. Plus high order terms. And for lambda equal to pi over 4, we can find this u can be written in this way. I C daga C, B daga minus A daga, B minus A over 2 plus high order terms. And this could be written in terms of exponential. That's the exponential that we have. Okay. So I'll let the details between these equations for you guys. It's homework over 2. Okay, so this in blue is homework. So homework. So okay, I don't know about the time. We have more than 1 hour already. I would like to finish this, but we could like do the next week, because I will have some discussion about this Fredkin gate, but I don't know. I think
Berend had a question that's kind of a digression. Can nonlinear Kerr media be used in a truly nonlinear way? In machine learning, we need nonlinear activation functions. This would be for the end of the discussion today.
yeah, this. I mean, when we say nonlinear median here is nonlinear in terms like in the last lecture, that we consider like the higher order terms in the polarization vector. This will give like the nonlinear dependence, but it's like inside the material. I don't know about the when we say machine learning, what is actually because the material in general, they are non-linear, right? It's not linear. Linear is just a first approximation.
Yeah, I think you may be confusing an analog quantum computer where you can look at all of the states in between with the gate-based digital quantum computer. But I understand Baron's question in machine learning terms. You have these nonlinear, what might be considered sigmoid functions at a low level.
Well, you also, sorry if I comment, you also have them when you do a hybrid quantum machine learning, because the problem with quantum is obviously linear. And let's say when you feed data, classical data into a quantum computer, whatever it is, you need to first carry out some kind of nonlinear function to kind of separate the data better. So it could be a tangents or whatever function, and then the rest is all linear in the quantum computer. So I was just thinking, would it be possible to do something entirely in quantum or optical rather than having a sort of classical calculation at the beginning before you feed those data into the quantum computer? Or
Yeah, I'm not so sure if I.
Yeah, that's
because the idea here. Let's just. I'll finish this because we have still some calculations to do.
Mm.
That I'll like to. I mean, not today. I'll finish like this box 7.4 and the next Friday because of the time today. But I think the idea here is doing computation like when we have the modes come here, do the nonlinear terms that we have here, the photons can interact. That's the thing. These photons that come here, photon A1 and B1, they could interact here. And this interacting do the nonlinearities here in this material. And we see this an example of this in the next. Maybe you could return to your question, Baron. I don't know well how to answer now. I'm not sure that I totally understood. But maybe in the next, with the examples that I'll show, because my idea was like to finish this box today, but I can finish the next Friday, and we do like an exercise to finish this topic. The exercise is this one, where we have like the Deutsch-Jozsa quantum circuit using like the Kerr media. So basically, this is the question here, the problem. He has to use this and to define this U here is he gives like the input 1 0 0 1, and we'd like to see the output with different U that you can like choose here using like the Kerr media, using something like this.
yeah, Carlos, I mean, maybe I'm misunderstanding something, but I was just thinking about the basic principles in quantum machine learning, and you always have to do something non-linear before you do the quantum computation, because quantum computations are normally entirely linear.
Yeah, because but I mean, but in the material here that we're using like this non-linear properties, but because this is this is due like the properties of the material. The material itself, like the slab that you use here, is like non-linear. When you say like, okay, quantum mechanics is linear, but this depends of the medium that you are considering. If you are inside that medium, this medium is classically non-linear, like this here. And so this will have the effect in your quantum system.
Yeah,
I-
okay. I mean, I was just thinking maybe it can be exploited in such a way
Yeah.
that there's something non-linear, that we have some kind of activation function that obviously would be at the beginning of the circuit, I guess.
Yeah, because I mean, photons will not, because the linearity, they will not interact if we are in the vacuum, for instance. But it could have this interaction if it's like in a weak interaction, depending on how how strong is your uh, non-linearity effects that you have in the media. So it could interact. This is one
Yeah.
of the drawback that you will comment here. But we discuss this in the next.
Yeah, thank you, Carlos.
And we can return like your question, because I'm not so familiar with the even I know the basics about like quantum machine learning. So I'll
I-
read something more maybe.
Yeah, I'm not sure that running the activation functions is the most computationally expensive part in the classical machine learning, but I might be wrong on that.
Yeah, right. That's okay. Let me just stop the recording. So we stop here today. I will finish like this discussion about this Fredkin gate, because it will be important to solve this exercise. Okay, this problem, exercise 7.13. I think this is interesting because it's like a practical. We are like see physically what is happening when we're solving like this quantum circuit associated with the Deutsch-Jozsa problem. So let me stop recording. Okay, see you guys in YouTube in next Friday. Yeah, Bumblebee is not here. I don't know if
He's been popping in and out.
yeah, I don't know if he would have some announcement, but since he's not, so I will stop.
Thank you,
Otherwise,
Carlos.
the video will be too big. Okay.